We get to do some worked examples on Archimedes principle. This first one goes: a concrete block of mass 2.7 times 10 to the power 3 kilograms, and the volume of that is totally immersed in seawater of this density. Find the weight of the block in air, and draw to the weight of the block in seawater. Now let's first remind ourselves that this should always be running at the back of our minds, that when we are dealing with Archimedes principle, the weight of the fluid that has been displaced is equivalent to the upthrust that has been experienced by that body that has been sunk in the fluid, either wholly or partially. So to begin off with Roman 1, weight of the block in air, of course this is more straightforward. We know that weight is given by mass times gravity. What is the mass of this concrete block we are talking about? The mass is 2.7 times 10 to the power 3. So it's 2.7 times 10 to the power 3 kilograms. Multiply that by the gravity. In all my videos, I'll be using gravity as 9.81. So this is going to give us 2.6487. Multiply that by 10 to the power 4 newtons. So that is the weight of the block in air. Unless otherwise stated, in all my videos, the value for G or the value for gravity will always be 9.81. So that's Roman 1 answered. So let's look at what the weight of block in seawater is like. So let's call this our seawater. We have this block in this seawater. Of course, now when this block is in seawater, it's experiencing what kind of force is it experiencing? It is experiencing an upthrust force. Let's call it that upthrust force. That is the force acting upwards. Then it also has the force acting downwards, and this force acting downwards is the force due to its weight. So of course, now that it is in seawater, it is having this force, its weight acting downwards. That is the weight when it is in air, acting downwards, versus its upthrust, the upthrust force acting on it upwards. The difference between these two forces is going to give us the weight of this thing when it is in the fluid. In other words, what I'm trying to say is that when this thing, before this block was immersed in this fluid, it was at first dangling in air. When it was in air, its weight is what was acting downwards. Its weight in air. It was acting, its weight, it is just its weight in air that was acting downwards, and upwards there was no force. Then we get this block with its weight still acting downwards. Then we come and dip it in water here. When we dip it in water here, it experiences now another upward force acting on it. So it means that this upward force, the upthrust force, is going to counteract some of this weight acting downwards. So when it counteracts some of it, it means that this block is going to lose some weight. That is what we call the apparent loss in weight of this solid. Now that apparent loss in weight of that solid means that this weight, when it was in air, has been reduced to a new weight. That new weight it has been reduced to is what we are calling the weight of this fluid when it is dipped in the seawater. So it means that for us to get the weight of the block in water, we are going to say weight in air minus the upthrust. So what is our weight in air? We already got our weight in air in our previous calculation. That was Roman 1. Our weight in air, we got it as 2.6487 times 10 to the power 4. So our weight in air is 2.6487 times 10 to the power 4. So that's going to be minus the upthrust. Now the issue here is that we do not know the upthrust. So it means we need to first go and first get the upthrust. After getting the upthrust, we come back and deal with this. Is the same as the weight. And we know that weight of the fluid displaced is given by mass times gravity. What is mass? The mass of this block, the mass of the fluid that has been displaced. Of course, we do not know the mass of the fluid that has been displaced, but mass is given by density, that is the density of the water, because we are dealing with seawater, right? So density of the water, multiply that by the volume of the water, and multiply that by the gravity. So of course, this is going to become, now the density of the water, the question says that the density of the seawater is this. So it's 1.03 times 10 to the power 3. Multiply that by the volume of the water. Now the volume of the water of the water that was displaced is equivalent to the volume of the concrete block that is displacing the water. And according to our question, the concrete block, they tell us, is of this mass, and the volume of that concrete block is 0.93 meters squared. So if the volume of the concrete block is 0.93 meters squared, it means that that's the same volume that was displaced, the volume of the water. So it's going to be times 0.9 times 10 to the 0.9 meters cubed, multiply that by gravity, which is in this case 9.81. And so our answer there definitely is going to be 9093.87 newtons. This is our upthrust force. Now that we've gotten our upthrust force, we can go ahead and finish up with our earlier calculation. Our calculation required us to find the weight of the block in water, which is the weight in air minus the upthrust. In this case, this is going to become 2.6487 times 10 to the power 4 minus the upthrust force, which is right there, 9093.87 newtons. And definitely that's going to give us 1.74 times 10 to the power 4 newtons, and this definitely is the answer, and it is the weight of the block in water. And in some cases they might ask you to find the tension. If this block was tied on a string, what is the tension in the string when this block is immersed in water? The tension that is experienced in this string when this block is immersed in this water is the same as the weight of that block when it is actually in water, which so happens to be this. A string supports a solid of mass 5 kilograms, and this string is a string supports a solid of mass 5 kilograms totally immersed in a liquid of density 800 kilograms per meter cubed. Find the tension in the string if the object has a density of 2575 kilograms per meters cubed. This question is related to what we've been doing earlier. Let's summarize it, or I like drawing diagrams to get a clear picture of what I'm up against. So this is a string. This is a string. It is supporting a solid of mass 5 kilograms. So it means that the mass of this solid is 5 kilograms. And the density, it's in a liquid of density. So this thing is immersed in a liquid. And the density of the liquid is that. So the density of the liquid is 800 kilograms per meter cubed. Find the tension in the string. We need to find the tension in the string if the object has a density. So the density of this object, let's call it the density of the solid, is given by 2575. That is kilograms per meter cubed. Now again, this string is supporting this solid. This solid is already here in the liquid. So the tension that is experienced by this is equivalent to the weight of that block when it is in this liquid. So if we want to find the tension experienced by this string, we are simply going to find the weight of this block when it is in the liquid. So we get started with the working. Of course, we know, like we had done in our earlier question, that for us to be able to find the tension in this string, it is the same as the weight of this block when it is in the liquid. And getting the weight of that solid when it is in the liquid, it's the same as getting the weight of this block when it is in air, which minus the upthrust. So weight of that solid when it is in the liquid is going to be given by the weight of that solid when it is in air minus the upthrust force. And this is still going to be given by, now what is the weight of this thing when it is in air? We have mass. We have the mass of the solid. We do not have the weight. But we can still find the mass. We know, okay, we got to find the weight of this. The weight of this solid when it is in air is given by 5 kilograms, multiply that by the gravity, which is 9.81. So we come and put that here. So this is going to be 5 times 9.81. That's the weight of this solid in air, minus the upthrust. Now, of course, we do not know the upthrust, but we know that upthrust is equivalent to the weight of the fluid displaced. So we continue with our working. This is going to be 49.05 minus the upthrust. Now, upthrust is the same as weight. So this is going to become 49.05 minus the weight of the fluid displaced is the mass of that fluid. Let's call it the liquid instead. Mass of the liquid, multiply that by the gravity. This is going to be 49.05 minus the mass of the liquid is given by the density of the liquid, multiply that by the volume of the liquid, then multiply that by gravity. This is still going to give us 49.05 minus the density of the liquid is given by 800. That's the density of the liquid right here. It's 800 kilograms per meter cubed. Multiply that by the volume of the liquid. Of course, the volume of the liquid that has been displaced is the same as the volume of the solid itself. So if we get the volume of this solid, then we know the volume of the liquid that has been displaced. So now what's the volume of this solid? The volume of this solid, according to our question, has not been given to us directly, but we have some information that can help us get the volume of this solid. If we maybe do some volume is going to be equal to, we know that density is going to be mass over volume. So if we make V the subject of the formula, we know that volume is given by mass over density. So and according to this question, we do have the mass of this solid. The mass of the solid was given to us here as 5 kilograms. And we also do have the density of this solid, and the density of this solid was also given to us right there. So if we get the mass of the solid and divide by the density of the solid, we will be able to get the volume of the liquid, because the volume of the liquid that has been displaced is equivalent to the volume of the solid that displaces that liquid. So the volume of the liquid here, let me first write the initials here. It's going to be equal to the mass of the solid, divide that by the density of the solid, multiply that by gravity. So we continue with our calculation. So this is going to become 49.05 minus, this is giving us 800, multiply that by the mass of the solid. Of course, the mass of the solid is 5 kilograms, so it is into 5, divide that by the density. The density is 2575, so this is going to become 2575, multiply that by 9.81, like that. So definitely computing this whole thing is going to give us 33.81 newtons. So 33.81 newtons becomes the tension. This becomes the tension in the string. There is an alternative way of doing this number that I would like to show. Remember one of our formulas from our previous workings? We know that relative density of a liquid is given by the upthrust experienced by a solid when it is in the liquid, divide that by the upthrust experienced by a solid when it is in water. And this upthrust, we are talking about the apparent loss in weight of that solid when it is in liquid, given by the apparent loss in weight when it is in water, the solid. So this is given by, of course, it's given by the weight of the solid when it is in air minus the weight of that solid when it is in the liquid. Divide that by the weight of that solid when it is in air minus the weight of that solid when it is in water. That is relative density of the liquid. Now, right here, now if you look at that formula, look, the question says, requires us to find the tension in the string. And the tension in the string is the same as the weight of that solid when it is in the liquid. In this case, our liquid here we are talking about is seawater. In this case, our liquid we are talking about is a liquid of density 800 kilograms per meter cubed. So now this is the liquid we are talking about. So the weight that is the weight of that of the solid mass when it is in the liquid is equivalent to the tension that is experienced in the string when that solid mass is in this liquid. So if we get this WL, the weight of the solid mass when it is in the liquid, that is equivalent to the tension. But now the question is that for us to be able to get this term, are we able to find the weight in air? Yes, we have the weight of the solid in air. We already have it actually here. The weight in air is 5 times 9.81. So we can get this term. We can get the relative density of the liquid. Remember, the relative density of the liquid is the ratio of the density of the liquid to density of water. We have the density of this liquid already. It's given as 800 kilograms per meter cubed. Divide that by the density of water, which is 1000. So we can get this figure. So we can also get this figure. Then there is this, the loss in weight in water. Now, of course, the weight in loss in the upthrust that is experienced in water, or the apparent loss in weight of the solid mass when it is immersed in water, we can still get this term by looking at the formula for relative density in a solid. Relative density in a solid is given by the density can be given by the weight of the solid in air, divide that by the apparent loss in weight, which is this when it is in water, and you can get this. So let's get started with the working to get this. Let's begin by getting the weight in air, which is obvious. Of course, our weight in air is given by the weight of the solid mass in air. The weight of the solid mass in air is given by 5 kilograms. Multiply that by 9.81, and definitely that we already got that as 49.05 newtons. So we have our weight in air. So let's go ahead and find the relative density of the liquid. We also know that relative density of the liquid, from the definition of relative density, it's going to be the density of the liquid, divide that by the density of water. That is going to give us the density of the liquid, which according to our question, the density of the liquid is 800 kilograms per meter cubed. So it is 800, divide that by the density of water, which is a standard 1000. So this is going to be 0.8. So that's the relative density of the liquid. So looking at our formula here, we have the density, we have gotten that. Now we need to get this expression. The apparent loss in weight of the solid substance, or of the solid mass when it is immersed in water. So from still our formula for relative density of solids, we know that relative density of solids can be given we can get it in two ways. We can either get it by saying it's the density of the solid over the density of water, or we can still get it also by saying it is the mass, or the weight of the solid when it is air and in air, divide that by the weight of the solid, the apparent loss in weight of the solid when in water. Now the apparent loss in weight of the solid when it is in water is what is WA minus WW, WA minus WW. This is what we want. We want this expression, this one. So this is going to be given by, now of course the relative density of solid is, we have the density of the solid already in the question. Do we? Yes, the density has, the object has a density of 2575. So this is density of the solid is going to be 2575. Divide that by the density of water, which is 1000. This is going to be equal to its weight in air, which we got. Its weight in air, we got it as 49.05. So this is going to be 49.05. Divide that by this, WA minus WW, the apparent loss in weight when it is dipped in water. And this is what we want. When we make this the subject of the formula, this is going to become WA minus WW is going to become 49.05 times 1000. Divide that by 2575. So now that we've got the expression here, we go back to our original expression. Our original expression is right there. Let me write it here. Now we already got our relative density in the liquid as 0.8 right there. So right here we have 0.8 is going to be equal to our weight in air, the weight of the solid substance in air, which is 49.05 newtons, minus the weight of the solid substance when it's dipped in the liquid. Divide that by WA minus WW. We got the expression for that as, which is 49050 over 2575. So we work towards changing the subject of the formula, because when we make this WT the subject of the formula, this is the same as the tension. So when we multiply this on both sides, this becomes 0.8. The weight of the solid substance in the liquid is the same as the tension we are looking for. When you compute this, you're supposed to be getting 33.81 newtons. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.